So hydraulics, such as the situation we've drawn here, where you have a hydraulic lift lifting a car, uses something called Pascal's principle, which says that a change in pressure at any point in a fluid is going to be, an inflow fluid at rest, is going to be transmitted to all points in that fluid undiminished. In other words, whatever change in pressure I put over here is going to be transmitted through the fluid and put over there. So in other words, I'm going to create a pressure. Pressure is force over area. So I have force 1 over area 1. That creates this pressure. That creates a pressure right here in the fluid. That pressure is going to be travel through the fluid to this point over here. So now at this point I have that pressure, and that pressure again, same pressure related to force 2 over area 2. What this means is that if area 2 is much bigger than area 1, then force 2 has to be much bigger than force 1. So if I put a little force over here, push down on this piston, I can lift a really big force, such as a car, over there on that really big piston. The good question now is, how does this actually work? So it seems like magic. I can put a really small force over here, say 100 pounds, and lift a 2,000 pound car over there. That seems a little far-fetched. However, thinking about forces is not the right way to think about this, because in terms of physics, there are some conservation laws: conservation of mass, conservation of momentum, conservation of energy. There's no such thing as conservation of force, so force doesn't necessarily need to be the same on this side and that side. But what does have to happen is we need to have conservation of mass. So in conservation of mass, we're looking mainly at volumes, incompressible fluid, so same density everywhere. So this really only works with incompressible fluids. You want the most incompressible fluid you can. That's how hydraulics works. Hydraulic fluid is very incompressible. So in terms of volume, area times this distance, so I have a cylinder, area times that distance, that's that volume there, V1. Here I have area 2 times that distance, that's volume V2. So this volume has to equal that volume. What that means is that since area 1 is smaller than area 2, delta x1 has to be much bigger than delta x2. So even if you want to push down with 100 pounds on this side to lift your 2,000 pound car, you have to push down a much larger distance. This might only go up 1 inch. You have to push down a foot to make it go up 1 inch. Because of that, then we have conservation of energy, which is the same thing as work. So work is a force times the distance. I'm pushing down F1 over this distance x1. That pushes up F2 over that distance delta x2. So conservation of energy says that force 1 delta x1 equals force 2 delta x2. If you rearrange that into force 1 over force 2, that's delta x2 over delta x1. But from conservation of mass, that's A1 over A2, and that is exactly Pascal's principle that we saw on the previous slide. So to do an example of this, I have a figure here, similar scenario, have some fluid, have a big piston on this side, diameter 5 centimeters, have a smaller piston on this side, diameter of 1.5 centimeters. But this time, this piston's connected to this big rod, hinged at this point, and so I'm going to push down 100 newtons at the end of this rod, and that's going to cause this piston over here to go up essentially. So for static equilibrium conditions, I'm pushing down with 100 newtons. How much can I lift on that side? So what is my F2 pushing down with 100 newtons? So two key concepts for this. First one is what we just talked about, Pascal's principle. So if I just look at the fluid, I'm going to have this big rod. It's going to apply some force on this piston. I don't know what that is because it's not 100. 100 acts over here. Show me some other force. I'm going to call it F1. So some force F1 pushing down on this fluid, F2 pushing down over there. Some area here, pi d squared over 4. Some area there, pi d squared over 4. So in terms of Pascal's principle, F1 over A1, F2 over A2. A1 pi d1 squared over 4. A2 pi d2 squared over 4. Pi's and 4's cancel out. I'm left with F1 over d1 squared equals F2 over d2 squared. So this force, unknown force F1, is related to F2 through the diameter ratio squared. Second concept we need to use is the fact that this bar is in static equilibrium. So if taking away everything else, only focused on the bar. And in terms of the bar, I had a force F1 pushing down that was acting on the fluid. In terms of the bar, I have an equal and opposite force from the fluid acting on the bar. So my F1 turned around. And so static equilibrium, sum of moments equals 0. take the moment around this hinge point here. So I have a force of 100 newtons, 33 centimeters away in the positive direction, and I have F1 3 centimeters away in the negative direction. So those two things have to add up to 0. So now just solve this equation to move F1 to the other side. Becomes positive. Divide by 3 centimeters, that becomes an 11. Then remember from the last reading, Pascal's principle, that F1 is actually F2 times d1 over dt squared. And so to find F2, just take this 1100 newtons, divide it by d1, which is 1.5 centimeters, divided by d2, which is 5 centimeters squared, and that gives you 12,200 newtons. So again, by pushing down this end of the bar 100 newtons, I can lift almost 12,000, actually just over 12,000 newtons for whatever was on that piston.